Good morning, everybody. Tomorrow, exam autopsy, right? Okay. And then today we're finishing up chapter 9. When's chapter 9 homework due? Is it this Saturday? Yeah, sounds about right. Okay, so we're right on schedule. Remember, I left sort of off with this a little bit, and I'm going to do plenty of examples today, but we just want to get it into our head. The chapter 9 toolbox, this conservation momentum thing I'm about to show you, the new part is here in the middle. We're going to be doing other physics on either side of these problems. And again, I'm going to model this, right? But just realize that we are going to reach for mostly conservation of energy. It tends to be the quicker, faster one to get stuff done. But let's just review real quick. How do you know if you need to do, say, kinematics? Yeah, okay. That time, if time is involved in any way, shape, or form, it's like 90% sure that that's kinematics. Time can also be power with energy, but generally it's that. And how do you know if you've got to do like Newton's second law? There's forces and some acceleration that's either needed to be known or given or something, right? Now, of course, acceleration can also be a part of kinematics, obviously. But if you want sort of the easier way, maybe, less cognitive load to deal with what's going on, I'd say try energy first. And if that doesn't work, then the reserve parachute would be kinematics or Newton's laws, right? Like, just try energy, and if energy doesn't, usually you can get energy done either quickly or fail at it really fast. Like, you'll find out, oh my gosh, there's no time here, something's gone wrong, so I'll try something else. So again, what we've learned so far about impulse, momentum, all that sort of stuff is right there in the collision. It's usually a very short time. And then there's other things going on either side that we've got to keep track of. Okay, so let's do some examples. Just lots of examples today, hopefully helping you on your homework, helping you set these things up, so on and so forth, right? So do your best to be like present here, right? Because again, it's going to be recorded on the PDF. It's going to be recorded on YouTube. But let's like engage with the problem. And remember our steps, like our approach to everything. We start with what? We've got to get a picture, either in our heads or on paper, maybe a list of what we know and don't know. And because I've sort of primed you and prepped you for this idea that we're going to have kind of this sandwich, you might want to think of the visualization as like a before, during, and after scenario. Kind of have to sketch out the scenes of a movie, right? Or the frames of what's going on. So what does that look like? So I've got this thing called a ballistic pendulum. I've actually got a real ballistic pendulum over there. It's hard to see, but those are two cannon barrels that are pointed directly at each other. So the cannon on the left fires, so there's a cannon right here, okay? It fires into this cannon right there. So one's firing the cannonball, the other's catching the cannonball. And this apparatus is what allowed the British Navy to determine how fast their cannonballs were going, right? For a given cannon design, what was the speed of the cannonball? Which is important to know how far it was going to go and all that kind of stuff. So we're going to use this thing called a ballistic pendulum. And these were in use all the way up until radar was invented, but now it's easier to do with radar. But it's a great example of conservation of momentum and what's going on. Okay, so what does this look like? We have a block, a catcher, something that absorbs the bullet, okay? Or in this case, the cannonball, right? And it's attached to like a string. You can think of it as, it doesn't matter what its mass is or anything. And we have a cannonball that's coming along, right, at some initial speed. And then that cannonball embeds itself into that catcher. Bless you. And then the catcher and the cannonball together swing upwards. And so in this problem, right, we shoot a cannonball, it embeds itself, and then swings up to a height h. So if you had to sort of think of before, during, and after, where's the before frame in sort of like my picture? It's like kind of here, isn't it? Okay. Where's the after frame? It's after, like it's moved up, right? So where's the collision? Where do the two objects in our problem come together? Right in the middle. And I tried to draw it right in the middle. So your approach here, as you're fumbling around and practicing these skills and getting it wrong, and hopefully getting it wrong really fast so you can start getting it right, is to try to, like, okay, what objects do I have? It's going to be two. It's always two, maybe more, but usually two, okay? When do those objects like hit each other? When do they stick together? When do they bounce off of each other? The chapter 9 conservation of momentum principle happens only in that instant when they're interacting. It could be something happening before that. It could be something happening after that. But in that contact, right? So you can go through here if you want and just kind of label these, right? Like this is during, this is before, and this is after. Whatever works for you. Maybe drawing some sort of lines down, right? To sort of distinguish what's going on here. And then for strategy, like how do you okay, so you've kind of organized information. Let's see, did we look at the data? No? Okay. So what do we know? What do they tell us we know? The mass of the cannonball, right? I'll do M sub C, cannonball, okay. And the pendulum block itself, right? Mass of the block. So this is the mass of cannonball, just to spell it out so I remember. This is the mass, mass of pendulum, M sub P. I'm changing my mind on my subscripts here. M sub P, mass of pendulum. Okay, so we know those things. What's the other thing we know? The height. So this thing swings up. And if I were to label that, right, it would be this height right here, right? It kind of starts at a low point and swings upwards. So just kind of defining it. And of course, if I had the numbers, I would just put the numbers in. But I described it. Okay. Strategy. Start in the middle. Just, even if you don't know everything, start with the meat of the sandwich, okay? Start with the filling. Take the bread off, start with the filling. Because what's going to happen there is you're going to discover what pieces of bread you need to add, okay? So start in the middle, right? And work sort of both ways outwards. So let's start in the middle. The middle is this during where this cannonball is being caught. And what has to be true? Well, the initial momentum and the final momentum have to be equal to each other. This is a conservation statement. You'll notice, unlike energy, we don't have any other term here. There's no like work other or momentum other anything, right? It's just whatever we have to begin with is what we have to end with. And you want to, again, like energy, like any conservation statement, it's like I have initial momentum, but I have two objects, don't I? I have a cannonball and I have a pendulum. This is, what do we call that when we have like two objects and we're thinking of them together? A system. So I know a lot of you are like, Mr. Balogh, that word system on the test, it threw me, right? This system, okay, is what we choose it to be, which I know is confusing and I know causes angst and all kinds of stuff because I could choose everything. Yes, you could, but that would be a hard system to do. Try to pick the simplest system we can. We've got two objects interacting. Those two objects are my system. If later I have to kind of change that, well, I'll change it and try something else. It's the mass of the cannonball. Yeah, sorry, my handwriting is Atrocious. So what have I got? So initial momentum. What could I have? I'll spell this out in full this time, and then I'll start taking shortcuts later. What could possibly have momentum? I've got two objects in my system. So what could have momentum initially? The ball. Okay, so we have the momentum of the ball initial, right? And we could have momentum of the pendulum initially. Now, you and I know that the pendulum starts with how much? 0, right? So maybe at this point I can just go ahead and, right? Okay. And how do we know the pendulum has no momentum? It's not moving, right? Not moving. Excellent. Okay. And then afterwards, so they've collided now, and afterwards, what's moving? Both of them. Okay. So we could, whoops. So we've got the momentum of the cannonball final plus the momentum of the pendulum final. So I've sort of just mapped out that I've got two things in my system, and I'm going to add together their momentum before the collision, and then I'm going to add their momentum together after the collision. Okay. So now we can go. Does anybody notice what disappeared over the tops of my P's? Ah! Where'd the vectors go? They're going to go into the sign that we give for things that we know. When we know, say, a velocity, and we say it's a positive 5 going to the right, that means that we've assigned to the right as positive. Okay? And so if we have a velocity going the other way, and it's a known value, we will give it a negative sign. If it's unknown, we're just going to leave it as positive, and the sign's going to work out for us. So this is a little bit of a sleight of hand. You're like, Mr. Balogh, what about the vectors? What about the components? It's not so much components as it is be careful with your directions. If you are given the direction of something, and it's opposite what you're calling positive, you need to make sure you have the right sign on it. Again, I know that's kind of like, oh, what does that mean? As you practice, okay, you'll get more familiarity with what's going on. Okay, how do I write down momentum? What's the equation for momentum? It's a mass times a velocity, right? So now I've got to write this down for the ball initial, okay? Boy, I've really screwed up my... Mr. Balogh. That should be a C. Cannonball. Ugh. Okay, so this would be mass of the cannonball, velocity cannonball initial, right? Plus 0. I'll stop writing that now. And then what do I write down for the final here? Mass of cannonball, velocity cannonball final, plus mass of pendulum, velocity, pendulum, final. I'm really just putting in definitions now. I'm not even sure there was any major thought process going on there other than I know what momentum mathematically is, so I'm going to insert it.
When the two objects combine, wouldn't they have this?
Okay, yes. So now we do physics. Okay? We took a break, we did a little bit of math, now we're going to do some physics. Okay? Is there a different symbol I'm using for velocity cannon initial? I called it V0 up there, right? So personally, I don't like writing all those subscripts. It gets confusing. Can I just write V0 for that velocity cannon initial? I know what it is. Or no, I know what I want it to be. I'm going to try and find it. Equals, okay. And then Liam said, wait a second. What do we know about the speed of the cannonball and the speed of the pendulum after they collide with each other? They're stuck together, right? So what kind of collision is this? This is inelastic because they've stuck together. Okay? So we can go about this several ways. I'll do it in detail. Mass of the cannonball, and then I'm just going to write V. Can I write V, or do you want VF? For final. VF? VF feels better. Okay, right? plus mass of the pendulum VF, because both of these are the same. They're both VFs, right? All right, so could I then, just looking at it as an equation, can I factor that VF out? Yeah, right? I can take VF. And now, what is this saying right here? What is this V final times a addition of masses? It's the momentum of the combined object. So it actually doesn't matter how you want to think about this. You could think of the cannonball and the pendulum as separate things doing the same thing at the same time. Or, what makes more sense in my brain, is I think of this combined cannonball pendulum thing as its own mass going places, right? Either way, it came out to be the same. Okay, so problem solving. I'm still strategizing. Believe it or not, I'm still strategizing, right? I know it looks like there's a lot of math on the screen, but really, I've just been changing subscripts around and doing some physics to see what things are the same and what are not. What am I looking for? Yeah, we want that one right there, right? Yeah, we don't know this one. So I have to put my sandwich fillings away for a little bit. And I've got to go find some bread, right? I know the masses. What I don't know is that V final. And that V final is final where? In the middle of the sandwich. It's the speed that the cannonball pendulum object has right after the collision. The V final would be like this V final is like right there. It's not the V final after it swings up to the top. What's the speed after it swings up to the top? 0, right? It comes to a stop when it gets to its maximum height. So we have a speed up here of 0. This V final could be like a V initial for a completely separate problem. Is the collision done? In the red side over here, in the after side? Yeah, collision's done. The thing's going to be moving at some speed, I don't know, but it's going to get up to 0 and it goes through a height h. What toolbox are we going to reach for?
We don't have forces or time, so we're going to have to use the energy.
Energy. And when in doubt, what's your default answer? Energy. So what have I got now? I've got a chapter 8 problem where, in red, I have something that's swinging up like a pendulum. It goes through a height h. It starts with some speed that I don't know what it is, but I want, and it gets to a final speed of 0. So I'm going to make my final point up here. I'm going to make my initial point down here. I'm going to set my 0. Have I done anything that's different from the way I do chapter 8 problems? This is standard conservation of energy stuff, right? Notice I have put away conservation of momentum, right? It's on hold. I am now working on this after problem. I got to figure out. Okay, so let's see here. Work other plus energy initial equals energy final. Is there any work other? Like, is there any friction? No. Okay, so that's 0. So energy initial, what energy does it have down there? Cannonball comes in, and what does the whole thing start doing? Moving. So what kind of energy does it have? Kinetic energy. So 1/2 mv squared equals, okay, what kind of energy does it have when it swings up and stops? Potential energy, mgh. Okay, solve for v. Can I get rid of the m's? Nice. Can I get rid of anything else? No, I can't get rid of 2's. I can't get rid. Okay. So that's a v squared is equal to 2gh. And so v is equal to square root of 2gh. So if I do this now, if I go square root of 2gh and put a number in, well, I don't know why I wrote it again. If I put my numbers in that they would give me, right? Now I know what that v is. That was the v that it started with at the bottom, but that v is what? It's the v final for the middle of the sandwich. There's like a lot of initials and finals going on, right? Maybe use different color pencils or pens or something, okay? To keep track of which V final is which. Because back when we did chapter, was it 4? And we had that car that like rolled down the hill and then became a projectile. That was like the first time we encountered this idea where we could do a problem, find out how fast something was going, and use that as the initial speed for the second part of the problem. You're doing the same thing here. You're breaking these problems up into sub-problems, and your data will feed through. So I now know for the black part here, MC V naught, which is what I want, my V final is going to be the square root of 2gh. And then I have this. So now I solve for the initial speed. I'm going to get the combined masses divided by mass of the cannonball times square root of 2gh. So if you're given a pendulum type problem, this might work for it. You want to double check and make sure the setup is the same, right? But if we know how high something swings, and we know what planet we're on, and we know the masses of the cannonball, the projectile, and the thing that's catching it, we can find out how fast that cannon was going in the first place. And I know you're sitting there going, but Mr. Balogh, we don't ideally shoot cannons anymore, right? This seems like an antiquated example of what's going on, right? Where does momentum factor in to my like everyday experience? Well, we'll sort of go violent here, and we'll go into virtual worlds. Momentum in video games. It's all there. Did you realize that? So whether you're playing like, I'll date myself now. You're playing a platformer like Super Mario Brothers. I was really, really good at that game when I was young. Or you're playing a first-person shooter nowadays or anything, the game engines have momentum built into them, including like when things come into contact. How does the game engine know how fast, say, an object should be going after an impact? It's got to run a calculation, right? Okay, it's got to do something like this, okay? And now, to be fair, the physics in video games is like the physics of Hollywood. It's kind of overblown, right? Because I'll just tell you the naked truth. If we put real physics into video games or movies, it would be really boring. It just would be. Because not what you expect to have happen doesn't happen, okay? People don't fly backwards when they get shot. Cars don't launch off the ground just because somebody shoots their gas tank, right? Okay? That's all fun and cool in action movies and superhero movies, but it's not the real physics of what takes place. There it is. There's the real physics for anything catching anything. Now, if a football player is catching a football or is being tackled by another player, are they swinging up to a height square root of 2gh? No. I would watch football if that were the case, right? All the receivers are on strings, and if they get tackled, right? Okay. But so is the part of the physics here in the center sort of identical, whether it's like a cannonball going into a cannon catcher or a defender grabbing and tackling a receiver? Yeah, right? Okay? Because you've got two objects that are sticking together. In the case of the tackle in football, though, my other piece of bread would probably be more like there's work other from friction as they slide across the ground, right? And come to a stop, right? There's other things going on there that wouldn't be a swing up. But the idea remains, right? There's a collision in the middle, and then there's things going along on the outside. Okay, So I mentioned that problem where the car rolled down. I did it for a reason, because we're going back. Okay? This time, apparently this car and the person driving it is having trouble remembering to set the parking brake. Right? Some of you are looking at me like, parking brake? Yeah, don't forget to set your parking brake. I know you've got like automatic transmission cars and all that kind of stuff, but always set your parking brake. Okay, my father-in-law doesn't, drives me nuts. Whenever I drive his car, I set the parking brake and then he complains to me, my car feels weird. I'm like, turn the parking brake off. All right, so what the heck is going on? They didn't set the brake and they left it in neutral. Okay. Turn to each other and draw this picture together. Like, talk about how you're drawing this picture in real time. Okay? Go. You're practicing visualizing.
You're saying the car rolls down a slope, but we're not given a theta.
Mm-hmm.
Okay.
Mm-hmm. Mm.
But it is a slope.
Mm. And what do slopes look like in physics?
A triangle.
Yeah, right? Okay. So oh, because you're eating bananas. Okay. You don't need the bananas to be radioactive. You don't need the bananas to be radioactive.
But to be like super radioactive?
Oh, to be more.
Yeah, to get, yeah.
Okay. Okay. You do realize how many bananas you'd have to eat?
It's like an
Oh, way beyond that.
I think we can do that.
Yeah. In a day. No. You would die from gastrointestinal disease. Malnutrition. Did your drawing start like this? Yeah? Are you starting to, oh dear, you're starting to think like a physicist now. All hills are triangles. All slopes look like this. Yeah, okay, good, good. They gave us a 25-meter high hill. Where's that? Ah! I didn't get the right tool there. 25 meters high, like a vertical height, right? Okay. Okay, so if I asked you what is our system, if you had to identify the system in this problem, what would it be? Car and truck together, right? Like if there's two objects, they are the thing that we are going to keep track of. We're going to try to apply our tools to these objects. So our system, car and the truck, we're not going to worry so much like about the earth, okay, or anything else. It's the car and the truck. And so where does the car start? Somewhere up here, right? M1. Or do you want MC for massive car? M1, okay. And then where's the truck? Somewhere at the bottom. M2. Let's see. This time, car rolls down the slope, collides with the delivery truck. It doesn't say, but I'm telling you anyway. Sorry, yes. So some of you might have drawn a picture where it's like this. That's fair. I should have. I actually wrote this one. I did not write it clear enough. Rolls down a slope and gets to the level road and collides. How's that? Okay. Thank you, Elijah. Okay. So the car rebound. Okay. All right. So this is kind of like a before picture, isn't it? Because what does the car have to do? It's got to come down the hill, and then it's got to, right? And then, like, what's the after picture? So, like, we have like a before. We have this maybe, okay? And then we have a, like the collision happens. And then what's the sort of the after picture look like? Car is going back this way, maybe back up the hill, right? And the truck, we assume, like, it makes sense, doesn't it? It's not like the truck is gonna, like, the car comes down, boom, and the truck goes, right? No, like, we assume it's gonna be going that way. Okay? But that's kind of what we want to find, isn't it? Right? We're looking for that velocity truck final. Okay? I'm just going to call that V. Okay? All right. So I got sort of like my before, my during, and my after. I've got a sort of a picture down. I could write a list of what I know and don't know, but I'm not going to add my masses to the diagram. It's going to confuse me later. Okay? But do I know what M1 is? Yeah, M1 is 1,500 kilograms, and M2 is 5,000 kilograms, and my height is 25. Okay, so I've got all that down. So where do I start? What do I do now? What's my strategy? All things come back to food. I do the momentum sandwich. Where do we start? With the filling, right? All good sandwiches start with knowing what you want to put in them. Bananas? Sure. Banana and peanut butter? I don't like it's too sweet for me, but sure, fine. Honey, marshmallows. What happened to pastrami? I'm serious. Okay, anyway. I'm hungry. So we start here in the middle, right? We start right here with a conservation of momentum statement. I do like to write my vectors on top of that because it reminds me that I've got to be careful about direction.
Are we going to assume this collision is perfectly elastic?
If you're not told, then you assume inelastic. Okay? The problem doesn't say, does it? They're not sticking to each other, so our base assumption is that kinetic energy is not conserved here. So that's not something that we can use. It's not a tool we can use. Yeah. You will be told if it's elastic. And if you're not told it's elastic, then it's inelastic. All right. Okay, so in the collision, initially, what has momentum? What's moving? M1. So I'm going to write M1 V1 initial. And I'm going to write plus 0 to remind me that I know that M2's initial momentum is 0. It's not moving, right? But it's a system. There's two things here. Okay. After the collision, what has momentum? They both do. So M1 V1 final plus M2 V2 final. Now, can we do the trick where V1 final and V2 final are the same? No, these are not connected to each other. And so I've got to keep them separate, right? I can't factor anything out here. Okay, so I know all the masses, right? Do I know how fast the car is going right as it hits? No. Do I know how fast the car is going after the collision? Yes. Do I know V2 final? No. I want, so this is again part of my strategy, want to find that thing. Okay? But I need this to be able to do it, don't I? Everything else is known. I got two unknowns and one equation. That's not enough. So now to fulfill my needs, like pastrami on rye, I need to go find another way to do it, right? I've got to work work towards the bread. And which side of the bread are we going to work towards? Left or right? Left. The initial speed of this car as it hits the truck. Can I find that from what it's doing going down the hill? Yeah. Can I find it after the collision? No. So I need to be working on this left-hand piece of bread over here. Okay? So now again, hit pause on the chapter 9 conservation and momentum stuff. We are reaching now to chapters 1 through 8. What do we know? Height. Do we know anything about time? No. Right? Do we care about acceleration? Please no. Do we have any friction? Great. Okay? This is a job for conservation of energy. And we actually just did this problem over there in red. I will do it again. Okay? I will do it in blue this time. Okay? Or do you want it in red? I'll do it in red. Okay. Conservation of energy. 3 things. What do we need? Initial, final, 0. Initial, final, 0. This is my initial point. This is my final point. Where's 0? Down here. Are there any springs? Thank goodness no, right? So, if that's my initial, that's my final, I do work other plus energy initial equals energy final. No friction in this problem, so there's no work other. What kind of energy does it start with? Gravitational potential energy, right? Sitting up there at the top of the hill, mgh. What sort of energy does it have at the bottom? Kinetic energy, 1/2 mv squared. I want the v, don't I? I want to know how fast this thing is going at the bottom of the hill when it runs into the truck. The masses are the same. I got a 2gh equals a v squared, so my v is equal to the square root of 2gh. That's exactly what I got over there. What do you know about the speed of an object if there's no friction and it falls through a height h? How fast is it going to be going? Square root of 2gh. Again, that applies if there's no sliding friction. If there were sliding friction, what would we have to do? Work other, right? There'd be some additional things going on, right? But if an object is just falling through a height h, and I know I'm using that word falling weirdly, is this thing falling? What's the force that's making it go down the hill? Gravity, square root of 2gh. Energy doesn't care. It all cares about is the height, right? The change in gravitational potential energy is going to give you that speed every single time. Okay? So you're going to see square root of 2gh a lot. It's going to like keep cropping up, and you're going to be like, they keep seeing this all the time. Is everything the square root of 2gh? Well, actually, you probably have a 50-50 chance of getting it right on a test by just answering the square root of 2gh. Like if you have no idea, just pick. There's 2 answers, square root of 2gh or 42. One of those is likely going to be the right answer. Why 42? Hitchhiker's Guide to the Galaxy? Yeah? All right, yeah. Reading. It was something people used to do. Actually, Hitchhiker's Guide to the Galaxy, so for those of you that aren't aware, Hitchhiker's Guide to the Galaxy is a satirical, funny, sort of science fiction book. The premise of the story is that aliens visit Earth and have to destroy Earth to make way for an hyperspace bypass. And so all the people on Earth have like minutes to live. And one of the humans survives and goes and has adventures, okay? And there's 2-headed people, there's paranoid androids, there's a bunch of stuff going on in this book, but it's all satire about our modern world. In the book, the answer to life, the universe, and everything is 42. It makes sense, doesn't it? They spend all 4 books actually looking for the question. Anyway, you don't need to know. If you want better satire, though, read Terry Pratchett, the Discworld series. Oh my goodness, is that a good series. Start with The Last Hero. I don't know why this became book reviews with Mr. Balogh, but it just did. Start with The Last Hero. by Terry Pratchett. It's an allegorical story about a set of retired adventurers that are mad about being retired and they want to go back and have a final quest. And so they decide to return fire to the gods with interest. It's hilarious. It's absolutely hilarious. Anyway, okay. That's my book review. We should start a book club. Okay, what were we doing? Square root of 2gh. All right. Do I know what V1 initial is? Yeah, it's square root of 2gh, isn't it? M1 times the square root of 2gh is now equal to M1 V1 final plus M2 V2 final. Okay, you guys like that. We'll put the numbers in for you. So let's put some numbers in. M1, 1500. Oh, you know what? I'm gonna do this over here. 1500. Jeez. 1500 times the square root of 2 times Earth times, what was my height? 25 equals 1500. Okay, what do we put in for V1 final? -5. Why do we put in -5? Our square root of 2gh, which was our V1 initial, we put in as a positive number, right? Moving, and that's moving to the right when it collides. What happens to the car after? We are told it's moving which way? Rebounds, moving the opposite the initial direction. Trying really hard in this problem to clue your brain into the fact that you got to put -5 in. Why minus? It's going to the left. We called right positive. So we're going to put in -5. This minus sign, it's going to kill you. You've got to be on top of it. On top, it's a vector. Mind the vectors. Okay. Plus 5,000 times my V final. So you go and you solve that. I have no idea where is it. Is it? Before collision 9. That's not it. Here it is. I got 8.14.
I got that when I did that plus 5.
We got 8.14? Yeah. When I got all my math here, it looks like it's working. Yeah, because this is going to be positive when it moves over, right? So we're going to go with 8.14. And what, oh my gosh, what units, what am I looking for? Velocity. So what are the units of that? How do I know it's meters per second? I haven't used any units on the screen. Well, some. I did standard units, right? Masses in kilograms, heights in meters. I'm guaranteed to come out in meters per second. Check it. It's positive. What does positive mean? It's going to the right. Is that what we expect this truck to do? Yes. Absolutely. Is it kind of fast? So the car was going at 22.14 at the bottom of the hill. Now, the car did bounce off the truck, which means there was more impulse, a bigger change in momentum. Okay? But yeah, got to be careful about what you think. So the car's going almost 55 miles an hour when it hits that truck, and the truck is going about 15 miles an hour after the collision. So, and the truck wasn't that big compared to the car. The car was 1,500, truck, 2.5 times bigger. Not that big a change in mass. Oh, what's that? Where are we? Okay. I've used the word magic on the screen. What we're going to do, this is my love letter to mathematicians. Okay? So for those of you that are into math or you're math majors, whatever the case may be, this is your one treat in this class. I'm actually going to do something very mathematical. Okay? For the rest of us, you want the punchline. I'll box it when we get there. Okay? But I want to set up, so here's the problem. Your book, most textbooks, go into way too much detail. If you look in your book and any other physics textbook, you will see that there's I think there's 6 to 8 equations in this section alone, the section on elastic collisions. It's full of equations. And the problem with every single one of those equations is that they tend to be well, this is if the first thing is not moving, or this is if the second thing is not moving. Like there's a bunch of conditions and caveats on whether or not those equations work. What I want to do, what I want to give you, what I want to empower you to do is to solve every elastic problem you encounter. I want to give you 2 tools to solve every elastic collision. But to get there, you need to understand and appreciate the price that needs to be paid. Because there is a price. And many people have paid this price to get us to the point where we can live in happiness and joy when it comes to elastic collisions. So let me show you the price, okay? Because in an elastic collision, what do we know? What? Momentum is always conserved, whether it is elastic or not, right? Elastic and elastic, momentum's always conserved. But the big difference between the 2 collisions is that kinetic energy is also conserved in an elastic collision, meaning there's no loss of energy to any sound, deformation, sticking together, nothing. It's a perfect collision. So kinetic energy conservation would look like this, right? There's no work other, there's nothing else going on. So what's the problem? Okay, so in any elastic collision, how many objects minimum are there going to be? 2. Don't ever do 3. If you have 3, just, anyway, figure it out. So I've got 2 objects, right? And those objects, what are all the possibilities for how objects can hit each other? This is a ton, right? We could probably think of 4 right off the bat, right? This one could be stationary and this one could be hitting it from this direction, right? Or it could be over here on the other side going this way, right? Or swap that. This could be stationary, right? Or they could both be moving this way and hit each other. They could both be going this way and hit each other. What if this one's going right faster? Now, can they hit each other if they're doing this? No. Okay, so that's the one we know can't happen, right? But we want to handle every single possibility we can in as simple an equation setup as we can. So this is how we're going to do it. We're going to write down the whole enchilada, okay? M1, V1 initial. So the first one could have momentum. And the second one could have momentum. After the collision, they could both have momentum. What did I put a final on there for? Jeez. I'm 3 steps ahead in my brain. And okay, M1, V1 final plus M2, V2. Okay, so right, there's a state. They could be all of those things. How are we going to deal with the directions things are moving? Positive velocities if it's moving to the right. Let's just say that right now, okay? And negative velocities if it's moving, we got it. Okay, so that's how we're going to handle the vector directions on these things. Okay, conservation of energy. Okay, so the initial kinetic energy of the first is 1/2 M1 V1 initial squared. I don't like my life anymore because now there's just too many subscripts. Plus 1/2 M2 V2 initial squared equals, and then the same thing, but with finals on it for both of the, oh my gosh. Oh my gosh. Okay. Usually what we know, okay, don't always have to. This will work for anything actually. But typically what we know is we know V1 initial and V2 initial and the masses, okay? What we're trying to find are the final velocities. So how many unknowns do we have? 2. There's 2 unknowns. And look, there's 2 equations. Now, what are the unknowns? V1 final, V2 final. I've got them over here, right? So, normally, how would you solve 2 equations with 2 unknowns? Substitution, right? Or the other way of doing substitution is find both equations equal to, like, say, V1 and set them equal to each other, right? So, like, but let's do substitution. Let's do substitution. Okay, so what are we going to, okay, does anybody see the problem with substitution? What do you mean very long? Like, what's the issue? Ah! There's squareds here. Okay, so let's do a what if. Let's do a what if. What if we solve this for V2? Right? V2 will be equal to how many terms? There will be 3 terms on the other side of, right? If I move this over, there's 3 things over here, isn't there? So it looks like this. And now I substitute that V2 into here and it's squared. What happens when you square 3 things? How many terms do you get? 9. You get not. And there. Okay? That's what you get. Big frown. Do you see the problem? Just mapping it out. This turns into a horror show of algebra. Okay? You have waded into the algebra swamp and you are not coming back. You've sunk in there for all time. So, how do we do this? I want to show you a mathematical sleight of hand, a magic trick that can save you whenever you encounter things like this, where you have like mixed powers of the thing you're trying to find. You got linear terms and squared terms and quadratic. Oh my gosh, it can get really bad. Okay? But let me show you this mathematical sleight of hand. It's so brilliant. This is one of the few math tricks that I really, really appreciate. We're going to gather we're going to get all the ones on one side and all the twos on another. We're just going to rewrite some of our equations and make them look a little bit friendlier, okay? So that means I have to move the M1, V1 over to the other side, and the M2, V2 initial's got to go over to the other side. Okay, so I'm going to do that first. So this becomes M1, V1 initial minus M1, V1 final equals M2, V2 final minus M2, V2 initial. I swapsy-daisied here, right? Okay. This one went over there, and this one went over there, and they picked up negative signs, didn't they? Okay, so that's what I did. And then to just clean this up a bit, we've got common factors. That's V1 initial minus V1 final. And over here, I've got a factor of M2, V2 final minus V2 initial. Okay, so it just I gathered all the ones on one side and all the twos on the other. Okay, I'm going to do the same exact thing with the kinetic energy equation. What can I get rid of? There's 1/2s everywhere. Get rid of those. Didn't like them anyway. All right. So then whoopsie-daisy, this one over, and this one goes the other side. They pick up negative signs. So I got M1 V1 initial squared minus M1 V1 final squared equals M2 M2 V2 final squared minus, I can't say anything anymore. Okay, there we go. Factor, do the same thing we did before, M1 V1 initial squared minus V1 final squared equals M2 V. This has gotten worse. Oops. This is no good, Mr. Balogh. What the heck is going on here? The left-hand equation and the right-hand equation are kind of close to each other, aren't they? They're feeling a little bit close to each other. It's just, again, we have this problem with squareds over here. But if you reach back deep into your high school algebra or college algebra, and you're dealing with differences of squares, you probably, your brain had already gone to sleep, because we all know what happens in math class. Your brain shuts off, or you have like pain information. Did anybody remember what the difference of squares turned out to be? Like if you have an x squared minus a y squared, there was a different way to write this. X plus y times x minus y. What's the magic? It gets rid of the squareds. Doesn't it? Doesn't it? This property of the difference of squareds, I'll write this on the screen just for those of you that really want it. So x squared, minus y squared can be written as x plus y times x minus y. It's the identity. So what does this become? It becomes M1 V1 initial plus V1 final times V1 initial minus V1 final. I did that right? Yes. Because like V1 initial is like X, isn't it? And V1 final is like, okay. And then over here, same thing happens. V2 final plus V2 initial times quantity V2 final minus V2 initial. You're like, Mr. Balogh, this is getting bigger, not better. What are we looking for? We are looking for the two final velocities, aren't we? Where are they? They're sitting, there's one right there, and there's one right there. And they also happen to be there, and there, and there. No. Yeah, and there. I've put them in more spots, not less. Here's where the real magic happens. Did you know that you can divide equations into each other? For some people, this comes as like a new idea. You can form ratios of equations and the equalities remain the same. So what I'm going to do, you can't quite see it. I'm going to copy this. Copy. And I'm going to paste it. Isn't this fun watching old people do technology? And I'm going to drop it right. So what did I just do? I took this thing right here and I copy pasted it right here. And now I'm going to divide. I know. This is like, what? This is a fantastic mathematical shortcut when you can get it to work. You divide the left side into the left side. You divide the right side into the right side. If your brain is melting, I will never ask you to do this on an exam. Okay? I told you at the beginning, wait for the punchline, right? We're getting to the punchline. Punchline's important. That's what I'll ask you about on the exam, okay? I know there's some of you in here that are closet mathematicians, okay? And I want you to see the pain that one must suffer before you can get to all of these wonderful tools. All right. Does anybody see what cancels? That goes away, and that goes away, doesn't it? And what else? That one? It's like, don't be scared, it's okay. V1 initial plus V1 final is equal to V2 initial plus V2 final. What's in the box? Two things that you know and two things that you don't know, right? But I would wager that the thing in the box is easier than this thing up here. Yeah? So here's your choice. You can either solve every elastic problem by starting with this equation and this equation. I wish you the greatest of luck. We'll see you in years. Or you can start with this equation. This one's still there, still valid, and couple it with this equation. Which one looks simpler to do? Second one. So, for an elastic collision, you are going to use the conservation of momentum statement, and you are going to use this thing in the box down there. I call that thing in the box the magical momentum equation. Can you use it for every momentum problem? Only elastic. It works for every elastic collision. Does it work for inelastic collisions? No. Do not use this for inelastic collisions. This only works. But there are only two equations for elastic. Instead of the 6 to 8 that the physics textbooks will have in it, there's only two. Let me show you an example. I tend to write this one slightly different, just so you're aware. I usually write this as V1 initial minus V2 initial equals V2 final minus V2 initial. Did I do that right? V1. Yeah, because I moved the V2 initial over V1. You're right there. I'm sorry. Amari, you were absolutely right. V1 final. There we go. I usually write it that way. So if you see me writing it slightly back, I'll try to remember to use the one in the box. The box is V1 initial, V1 final, V2 initial. Okay. All right. So let's do an example. So we got two bowling balls. They are going to be in a head-on collision, right? So what does our picture look like? Bowling ball numero uno going that way, right? Bowling ball numero dos going that way. That's like the before picture, right? What would the during picture look like? Bonk. And then what would the after picture look like? Probably something like that, right? But we know what's going to happen, right? But what if bowling ball 2 were like a lot bigger, like way more massive? Would it bounce off necessarily? It might keep going in the same direction, right? So again, we don't want, the unknown things here are the final velocities of the object. So you can make a guess, but don't assign values or directions to those things. Let the physics and the math work it out. And then check to see your answer against what your intuition tells you. Okay, so I got kind of my before, during, and after. Now, for an elastic collision, again, it says assume a perfectly elastic collision. What are we going to do? What two equations are we going to use? Like your strategy is set. What's the strategy? Conservation of momentum, V2 final. Okay, M2, V2 final. So there's my conservation of momentum statement, right? That's bog standard, came out of the inelastic. It's the standard conservation of momentum, okay? And then what's the other equation we're going to use? the box, the magical box one, which doesn't have any masses in it. Darn it. V1 initial, V1 final, V2 initial, V2 final. Are there vectors here? Yes, but we're going to handle those vector directions with positives and negative signs based on what directions they're going, right? My advice, oh, okay, and by the way, both of these equations work for things that are standing still. What if V2 initial were 0? You just put zeros in, okay? There's no special equation for it. It's just, it works for everything. My advice, this is what I do. I know it's shocking. Just put the numbers in right away. Don't try to solve this symbolically, okay? Just drop the numbers in and go for it. The symbolic solution is done. That's it. Now put the numbers in. So, what's M1? 8. What's V1 initial? Careful. Plus 5. Why am I going to put plus 5 in? It's going to the right, and I want to remind myself that I need to do directions. Plus M2, which is 10. All right. It says that the heavier one's going at 2 meters per second, but what am I going to put in? -2. Got to get the directions right. All right, and then I have an M1 V1 final plus an M2. Those are numbers, Mr. Balogh. I have an 8 V. Can I just write V1? Because we know it's final. Okay. Plus 10 V2. So I've got that. Okay, we can clean up. 8 times, I don't know what 8 times is. 40? Yeah. And then 10 times 2 is 20. And so this is a 20. 40 plus a -20 equals 8V1 plus 10V. I really want to get rid of some stuff. So I'm going to divide by 2. 10 is equal to 4V1 plus 5V2. We got that about as simple as I want to make it right now. Okay, over here. V1 initial. What is it? Not 5. Positive 5. Plus V1 final. What is it? -2. Right? No. No, it's not, Mr. Balogh. It's just V1. Oh, sorry. V2 initial is what? -2. That's what I was trying to do. And then V2. Okay. Should we solve for V1? Find V1 first? Sure, why not? So that means I'm going to solve this second equation over here for V2. I'm going to solve it for V2, plug it in for V2, then I'm going to have V1s left over. Okay, so what does this look like? That's plus 5 plus 2 plus V1 is equal to V2, right? I move the -2 over, becomes a plus 2. 5 plus 2 is 7. And now this V2 goes in there, doesn't it? So this is 10 equals 4V1 plus 5 times 7 plus V1. 10 equals 4. 5 times is 35? Is that right? I don't know my times tables anymore. Okay. Plus 5V1. This is -25 when I move the 35 over, and this is a 9. So V1 is equal to -25 over 9, or 2.78, -2.78 meters per second. There's my V1. How do I find V2? Put it up there. 7 plus a -2.78 equals my V2. So my V2 is going to be equal to 4.22, positive 4.22 meters per second. Check it. What does a negative number mean for V1 final? V1 went left. What does a positive number for V2 mean? It went to the right. Does that seem reasonable? 2 bowling balls about the same mass. Are they going to bounce off of each other? Sure. Normally, I'm telling you things like read the book, do your homework, all that kind of stuff. Do your homework. Don't read this section. Those of you who have already read it know that there's lots of equations in it. There are only 2, right, that you need to do every elastic problem as long as you're careful with your directions, right? Make sure that you put in directions for things that you are given, but don't assign positive and negative signs to your unknowns. You just kind of leave them all positive. They will work themselves out. Check the signs at the end when you're done with your math. Are you going to use this method for inelastic problems? No. Inelastic problems, you're back to the sandwich. Okay? But for elastic problems, you're welcome, by the way. Have a great day. I will see you tomorrow. Exam autopsy time. Good morning.
Good morning.
I'm so glad you're here.
Yeah, I know, me too.
No, you're not.
Okay. I was gonna ask if I can go take test
Yeah, of course.
autopsy
Yes.
real quick because I just wanted to see what I did wrong.
Yeah.
But I'm not gonna do it. You know what I mean? Is that okay?
Totally up to you.
Okay.
Yeah, no, I would want to see what I did too. Yeah,
Okay.
yeah, all
Yeah.
that kind of stuff. No problem.
I know this